This experiment is about the operational amplifier, which we also call the OpAmp. Now, for this course, we do not intend to go into the internals of the operational amplifier, what goes into it, what it consists of, how they are interconnected, and what its performance actually is. We will deal with an ideal op-amp in the same manner as we did in the past, that we handled an ideal diode, which was a means of simplifying the concepts. So we deal with only an ideal operational amplifier here. Now I will not spend time on discussing the pinout diagram or other mundane details of the op-amp. All that is there in the manual and you will have to read the manual anyway. Now what I want to focus on here are the bare essentials that will help elaborate further on the experiments that you need to conduct. So the op-amp is drawn like this, and this is called the output. There are two inputs. The upper one is called the inverting input and the lower one is called the non-inverting input. So this is called the inverting and this is called the non-inverting input. In addition, other things that end up as terminals for the op-amp are two power supply points which supply plus VCC and minus VCC. So we will show that over here. And ground is another thing that will be implicitly required when we use the operational amplifier. Now, the most important thing I want to stress upon when you connect up the operational amplifier for use either in a linear or in a non-linear circuit is to take care that the polarities of the supply are connected properly. Plus VCC terminal should go to plus VCC, minus VCC terminal should go to minus VCC. Any kind of mistake in this will destroy the op-amp immediately. Furthermore, be very careful about identifying which terminal is which. Understand how to read a pinout diagram and how to interpret what is the first pin, what is the last pin, and the order and sequence in which the pins are counted. Having done all this by making use of the information given in the handout, we come back to the ideal op-amp and how it operates. Now, what does the ideal op-amp really do? The ideal op-amp is an ideal amplifier in many ways. Now I will list some ways in which this is considered an ideal amplifier. What are the fundamental features? A. Two inputs. The difference of which is amplified. That's the first important feature. Second, very high ideally infinite gain. Practically it's of the order of 1 lakh to 10 lakhs, that is 0.1 million to a million. C. This focuses on other aspects of being ideal that you would like any device to have, especially an amplifier. It does not draw power from the input side, that is, it has infinite input impedance. Of course, again, this is for the ideal op-amp. The actual op-amp will have very high but finite input impedance. The next nice feature, and the last that I am going to mention, is almost zero output impedance. That means it acts as, the output acts as an ideal voltage source, the input acts as an ideal load. An ideal load is one which doesn't burden the source to which it is connected, and that's why we say it has almost infinite input impedance. And it acts itself as an ideal source by not getting loaded or drooping its output voltage just because a load is connected. All this, of course, is within its recommended region of operation. If you take it out of the recommended region of operation by drawing too much current from it, applying excessive input voltages, etc., it will go into what is called saturation or exceed its limits of operation, and very rapidly all the ideal characteristics will disappear. So much for the introduction to the op-amp.
Welcome to experiment number 5. The name of the experiment is Study of OpAmp, Operational Amplifier Circuit and its applications. OpAmp is a basic linear integrated circuit which will have many applications in communications and related areas. Now we will show you how to connect the OpAmp IC in the circuit, and we will tell you about how to identify the pin and pin numbers. Now before connecting this IC into the circuit, we have to take some precautions. One of the most important precaution that we have to take while performing the experiment is that the plus 12 volt and minus 12 volt supplies are connected properly to the OpAmp pins, pin 7 and 4 respectively. That is plus 12 volt from DC power supply to pin 7 and minus 12 volt from DC power supply to pin 4. Interchanging of these connections will make the IC damage. So we should not connect this power supply connections to interchangeably or to other pins. And now we will show you the potentiometer. So this is a variable resistor. So we can vary the resistance using the potentiometer. Here we are seeing that 3 terminals are there for potentiometer. In between these two extreme terminals, we can get 10k resistance. And if we use this middle one also for getting variable resistance values, and we can get that variable resistance values by rotating this knob, that white one. So taking the connections from the first two, this one, and rotating this, we get the varying resistance values.
The first thing to understand from these properties that are listed over here is that it has very high gain, and because it has such a high gain, even a small voltage, a minuscule voltage applied directly to an op-amp configured in this manner will make it reach the maximum possible output voltage, which is called the saturation voltage, and which is approximately 90% of the supply voltage. So if it is operated at plus VCC of 15 volts and minus VCC of minus 15 volts, then the slightest positive voltage applied, the slightest positive voltage difference applied between these two terminals will make the output go to plus VCC. It cannot go higher than to plus saturation, VSAT, which is, as I said, around 13 volts if this is at 15 volts, if VCC is at 15 volts. It cannot go any higher than that because it is limited by the supply voltage. And the slightest negative potential applied between these two terminals will make it dip right down to minus VSAT, which is around minus 13 volts. So this is what will happen to an op-amp that is operated without feedback, what is called the open loop operation. Because of this, for functioning as an amplifier, it's not a very great idea to use an open looped amplifier. What we do is to make an op-amp behave as a linear device over a much larger input dynamic range by introducing a resistor, as we have done in this diagram over here, between the inverting terminal and the output terminal. Let's understand qualitatively what this does. If the output voltage tends to go up, then a portion of the output voltage is brought back and fed into the inverting terminal, thereby diminishing the input. And this makes sure that the output does not hit the saturation value as immediately and as hastily as it normally would in the absence of this resistor. So this is called the feedback resistor. It's called R2 in this case, and we have chosen this to be 51 kilo ohms. What this circuit does, and this is the first circuit that we will be making, is to create an inverting amplifier. If you apply a VI to it as the input, as we have shown over here, which is an alternating sinusoidal voltage within a reasonable bandwidth of say a few kilohertz, then the output will be minus VI scaled by some positive constant K. So the value of that positive constant is given by R2 by R1. So that VO equals minus R2 by R1 times VI. So this is the relation that governs the behavior of this circuit. Let us understand how this has been arrived at by analyzing this circuit. We have to keep in mind all the special properties that an op-amp has, that an ideal op-amp has, in order to analyze the behavior. Now, in the presence of feedback, we are entitled to make the assumption that the output is unsaturated. So, given that the output is unsaturated, we can conclude from the fact that the op-amp's open loop gain is nearly infinite that the voltage difference between these two terminals is nearly zero. Because nearly zero times nearly infinity alone will give you a finite number. And this is unsaturated, that means it is finite. If it is saturated, it's still of course mathematically finite, but that's only because it is unable to go towards infinity on account of the limitation of the supply voltage, the VCC. So as long as it is assumed to be unsaturated, we are assured that given the open loop gain being so high, the input terminals are very reasonably at the same voltage. That is to say that if this positive terminal or the non-inverting terminal has been grounded, this inverting terminal is also going to be at a voltage that is practically equal to the ground voltage. So this much analysis has been made on the basis of the very large open loop gain Okay? Now that we have the very large open loop gain, we will make use of the next nice property that an op-amp has, that is very large input impedance. So come over here again, we have this, and here this point now is to be at ground voltage, as we have just argued. If this point is at ground voltage and Vi is applied over here from an ideal voltage source, the current that would flow would just be Vi minus 0 by R1. That is the current that would enter R1, and that current would flow up to this junction point. Now we invoke the high input impedance property of the op-amp. Because the inverting and non-inverting terminals have nearly infinite input impedance, the current that has arrived here cannot enter the op-amp. It instead has to take this route and go into R2. It has to go into R2, travel all the way through and reach the output terminal. Now if it does all this, since the current is known, the current is Vi by R1, since this terminal's voltage is known, it's equal to nearly the ground voltage, we will say it is equal to the ground voltage. Then this point is below the ground voltage by a factor equal to the current times R2. In short, the current is given by Vi by R1 and the output voltage is given by minus R2 times this. So this is VO, and that is what the inverting amplifier does. The inverting amplifier essentially is an amplifier of adjustable gain. By choosing values of R2 and R1, you can implement any value of gain that you want as long as it is negative. So if you want, for example, a gain of 2, then instead of choosing R2 to be 51 kilo ohms, you choose R2 to be say 20 kilo ohms, given that this is 10 kilo ohms. Or keep this at 51 kilo ohms and make this around 25 or 25.5 kilo ohms. That will again make the gain equal to minus 2. So by choosing appropriate values, suitable values of R1 and R2, you can make an inverting amplifier with whatever gain you want. Remember that for an inverting amplifier to work as an inverting amplifier, the non-inverting terminal has to be grounded. That is the basis of determining that the inverting terminal is also at ground potential as long as the amplifier is not saturated. So this is how this circuit works. So you will apply different signals over here. You can apply triangle waves, sine waves, whatever you like, and observe the corresponding inverted signals on channel 2 of the oscilloscope on the other side. So much for the inverting amplifier. Now we move on to the non-inverting amplifier, and let me just make some space here by clearing some of these equations. Let's consider now the non-inverting amplifier. Since I have already been through the principles to a certain degree when I discussed the inverting amplifier, I can assume that some things have been understood. As I said, here too, since it's working as a linear amplifier, we assume that output is not saturated. As long as the output is not saturated, we can again make the assumption that the two input terminals are practically at the same voltage. And that means that if this point is at Vi as it has been connected to Vi, remember that it draws no current from the source because it has infinite input impedance. It kind of just sniffs the source but doesn't take a taste of it. This point is at Vi, and on account of the tight coupling between the voltage here and the voltage here, this is also at Vi. Now if this is at Vi and this end is at ground, you will have a current flowing outwards towards the ground of magnitude Vi by R1. Now that current has to flow because there is a potential between the two ends of R1. But being an op-amp, it neither sources nor sinks current at the inverting terminal. So who's going to supply the current? R2 has to supply the current. The current that is of magnitude Vi by R1 isn't coming out of this terminal, it's coming out of this path down here and through R1 to the output, to the ground here. Hence, let's estimate the value of VO now. This same current is flowing through R2 also. So, what will be the voltage of this point? This point is at voltage Vi, and this will be R2 times the voltage of this point. If this voltage is whatever, then this will be R2 times Vi by R1. But then this point is itself at Vi. So what you get is Vi plus Vi times R2 by R1, which is equal to Vi times, so this is VO. This is finally the equation that relates the output to the input. Here the gain is given by 1 plus R2 by R1, but it's a positive number because all the numbers inside the parentheses are positive. It gives you a positive gain of whatever value you have set, according to whatever value you have set for R2 and R1. You can make them large, you can make them small, based on the choices of R2 and R1. For example, choosing R2 to be 51 and R1 to be around 10, R2 by R1 is approximately 5, plus 1 makes it 6. So you have a non-inverting amplifier where the waveform of the output and the input have the same phase, but the output is 6 times larger than the input in this case. So this is an inverting amplifier. Now there are some points to notice. The non-inverting amplifier does draw current from the supply. It is not the op-amp itself which is taking the current away. That current is flowing from R1 through R2 and going towards the output and being sunk through the output terminal. But the fact remains that the input supply has to supply some current. The input signal source has to supply some current to the circuit, to the overall circuit. Whereas here, the input signal source supplies no current at all, ideally. It supplies no current at all, and yet its output gets amplified by 1 plus R2 by R1. Here the gain was minus R2 by R1, hence it was an inverting amplifier because of the minus sign. Here it's a non-inverting amplifier because the gain is 1 plus R2 by R1, R2, R1 and 1 all being positive.
Now we will see how op-amp can be used as inverting amplifier. Initially we have to make the circuit connections as shown in the handout. For this, first we will set 0.1 sin omega t in the function generator, that is a sine wave of frequency 1 kHz and amplitude is 0.1. So we have already set 1 kHz frequency. Now we will switch on the DC power supply, which gives plus 15 volts and minus 15 volts to op-amp. Plus 12 and minus 12 volts to op-amp. Now we will switch on the CRO. The connections are seen in the breadboard. Yeah, now you can see the input signal which is given from the function generator. The amplitude is peak to peak is 200 millivolts, that is 0.2 volts. So amplitude is 0.1 volts. The frequency is about 1 kilohertz, as we can see from the DSP. Now we will switch on the channel 2. After connections are made, give the output 6th pin of the IC, OpAmp IC to DSO. So this blue one shows the output of the OpAmps inverting amplifier circuit, and this yellow one shows the input of the inverting amplifier circuit. We can see that basically we can observe that the output of the OpAmp inverting amplifier is amplified than the input. We can see that we will measure the voltage. So it is showing around the amplitude of the output signal is around 5 millivolts. I mean 500 millivolts. It means 0.5 volts. So it gets amplified. So it's an inverting amplifier basically. So it is amplifying. And why inverting is because of the phase shift that we can observe. The input is not in phase with the output. It is shifted by 180 degrees, so that we can see clearly the difference. That's why it is called inverting amplifier. Now we will show. We will see this practically how this phase shift is going, getting 180 degrees in the X5 mode. So in the X5 mode, this is the x-axis input and the y-axis is output. So we can see the plot is a straight line but with a negative slope. The negative slope of this waveform indicates that it is an inverting amplifier which is shifting 180 degrees out of phase the output from the input. Similarly, we can perform the same experiment . After observing the input and output waveforms for inverting amplifier, in the X5 mode, the VA and V0 characteristics also. Now we are ready to measure the voltage gain AV of this inverting amplifier circuit. The formula for AV is given in the handout, which is V0 by Vi, where Vi is the input sinusoidal signal given from the function generator, which has amplitude of 0.1 volt and frequency of 1 kilohertz. And V0 is the observed output waveform from the pin 6. The V0 is turning out to be 0.5 sine omega t plus pi. So using the formula of V0 by Vi, we can calculate the voltage gain, and we can observe the sign of AV also. That turns out to be negative because of the inverting nature of this inverting amplifier. Now, for non-inverting amplifier also, we can repeat the same experiment that we will leave to you to perform the non-inverting amplifier part. In the non-inverting amplifier also, you should connect the circuit as shown in the handout and observe the waveforms V0 and Vi even in the XY mode and measure the voltage gain. The one feature that you are going to observe is that the output is in phase with the input. That shows the non-inverting nature of the amplifier. In the same time, the output signal gets amplified.
Until now, for the first two experiments of the inverting and the non-inverting amplifier, we believed that the op-amp was actually ideal. In this experiment, which is also a linear use of the op-amp, we will try to see how much the given op-amp, the practical op-amp on the table, differs from what is considered ideal behavior. So that is what we are going to focus on in this experiment. Well, what do we know about the op-amp? We know that it amplifies the difference between the voltages applied to the inverting and the non-inverting terminals, or rather vice versa, between the non-inverting and the inverting terminals. From this it follows that if I apply exactly the same voltage to the two terminals, then the output must be identically zero. Does this happen? Now, in an ideal op-amp, this is what is supposed to happen. But in a practical op-amp, the kind of perfect balance that ought to exist between the inverting terminal, input terminal and the non-inverting input terminal does not really accrue. So you will find a small amount of non-zero gain called the common mode gain or AC even when practically identical inputs are applied to both the input terminals. So we call that the common mode gain. A common mode. So how do we evaluate this? We set up this circuit that I have drawn over here. And let me explain what this is. There is this supply which is producing a voltage Vi, which is being applied in parallel to these 2 points. And these 2 points lead through 10 ohm resistors to the inverting terminal on the one hand and the non-inverting terminal on the other hand. Now, what is the voltage observed at the non-inverting terminal? It is Vi times 47 plus X times 10 to the power 3 divided by 47 plus X plus 10 times 10 to the power 3, where X represents the resistance of the potentiometer over here. This is X because it's adjustable, it's not a fixed value. So this is the voltage. This is not Vi actually, this is Vi times this is actually V plus, the voltage experienced at the positive terminal, at the non-inverting terminal, input terminal. Now by a similar arrangement on the inverting side, we seek to apply practically the same voltage on the inverting terminal as well. But then, why this potentiometer? Why this choice of 47 kilo ohms? These things need to be explained. And they are easily explained. The fact is that none of these resistors are exact. You have already seen in the second experiment that components are only perfect to within a certain tolerance, 5%, 10%, 1%, etc. So given this fact, unless we take precautions, we cannot be certain that if I put a 51 kilo ohm resistance instead of the combination of the potentiometer and the 47 over here, just as I have put a 51 over here, it would be the case that V plus and V minus are equal. It would not be the case because this is called 51 kilo ohm. It could be anything between 49 and 53 kilo ohms. This, on the other hand, could also vary between 49 and 53. This 10 kilo ohm could be anything between 9 and 11. This 10 kilo ohm could be anything between 9 and 11. So you can see all the possibilities that ensue from this sort of variation in the resistor values. And these variations would, in spite of having applied the same input voltage in parallel to these two terminals, these variations would ensure that not exactly the same voltages appear here. In order to balance this out, what we do is this. Let this be 51, nominally 51, actually maybe 53 or 52 or 51 or 50 or whatever. What we do here is take a value slightly less than this and keep a remaining part which is adjustable. And then we go by the principle of operation of the op-amp. What does the principle of the operation of the op-amp say? It says that when the inputs are identical, the output should be 0. Modified to apply to a practical op-amp, we will say that when the inputs are identical or as close to identical as possible, the output will be as close to 0 or as small as possible. So, we connect this to one channel of the scope, we connect this to the other channel of the scope, and we tweak this potentiometer until the sum of these two resistances, or rather this potential divider ratio, and hence finally this terminal inverting non-inverting terminal voltage becomes exactly equal to the inverting terminal voltage. Remember that all these are only correct to within a tolerance, and it is given all these possible variations that this potentiometer gives you the handle to ensure a perfect balance for some particular setting of it. And at that particular setting, the output ought to have been 0 for an ideal op-amp, but it isn't 0. It is an extremely small voltage. Now if that small voltage is what we call VOC, not for V open circuit, but VO under the common mode, and this is divided by VI under the common mode, this gives you the common mode gain, which we call AC. Common mode gain, when evaluated, will turn out to be slightly greater than 0. It will not really be 0. At least its modulus, or rather this quantity, will be something slightly greater than 0. It will not be 0 as it ideally ought to be. Now, we operate the circuit in what is called the difference mode, where we actually try to apply a voltage which is different at the inverting and the non-inverting terminals. And how do we ensure that? Very easy. We just disconnect the inverting terminal from the supply and ground this inverting terminal. So the inverting terminal gets 0, the non-inverting terminal gets a voltage at the non-inverting point given by Vi times this, because this part hasn't changed. Now if this is the input, we measure what the output is. Now, as long as the op-amp is not saturated, and it is not going to saturate very quickly because there is this feedback resistor still present, we can be sure that there will be a lot of gain this time. It will not be AC, which is greater than 0 but pretty close to 0 as it should be. It will be a reasonably large positive number, and that number is what we will call AD. Difference mode gain is given by VOD by VID. Difference mode output by difference mode input. Finally, when we have these two values of the difference mode gain and the common mode gain, we construct a figure of merit of the actual op-amp's performance. For an ideal op-amp, AC ought to be 0. So if you really divided AD by AC, this should be equal to infinity. But for a practical op-amp, it will not be infinity but a reasonably large number called the CMRR, which is the common mode rejection ratio. In the experiment that you will carry out in the laboratory, you will first construct the common mode circuit which I had shown you earlier, where this supply was jointly applied to both the terminals through their respective resistors. Evaluate AC. Then disconnect, ground this inverting side, and then apply an input only to the non-inverting side and get the differential mode gain. Then evaluate finally AD by AC, which is the CMRR. The larger the CMRR, the better the op-amp is said to be.
Now, we will study the performance of difference amplifier by measuring its common mode and differential mode gains. For an ideal difference amplifier, differential mode gain AD is infinite and common mode gain AC is 0. Thus, we will get infinite CMRR. CMRR is equal to AD by AC. So when AC is 0, CMRR becomes infinite. But practically, for practical OpAmp circuit, AD is finite and AC is not exactly 0. So our CMRR is not going to be infinite, but in the order of 10 to the power of 4. Okay, now we will measure the common mode gain and differential mode gain. Starting with common mode gain measurement, we have to connect the circuit for common mode gain AC as shown in the handout. So we can see here the circuit connections are made, and for this circuit, actually in the handout in the figure 6C, for the resistor, R1 resistor is grounded at the one end, but for common mode, for measuring the common mode gain, we have to supply same voltage Vi to both the ends of R1 and R3. Now we will give input signal of 10 volt amplitude and 1 kHz sinusoidal signal from the function generator to the R1 and R3 ends, and we will observe the output voltage from the 6th pin in the DSO. We can see that there is a 10 kilo ohm pot here. This is a potentiometer. We have to adjust the potentiometer such that the V0, which is shown in the blue color, that waveform, the amplitude of it should get reduced. So adjust the potentiometer. Now we are going to adjust it such that V0 is reduced. For knowing the value of V0 while adjusting, please press the measure button. Now we can see Vmax here for second channel. The output is given in the second channel, input is given in the first channel. For the second channel, reduce the output as much as possible. It is showing 120, 80, 40 like that. So it's almost, it's very less, showing around 9 millivolt, 10 millivolt. We can reduce it as minimum as possible using the pot. Now after setting potentiometer, keep it unchanged and find the common mode gain AC, which is given by V0 by Vi. Note down the value of V0 and Vi as well, and find the common mode gain. Now we will measure the differential mode gain AD. For this, little modification the circuit is needed. That is, remove the input Vi from one end of R1 and connect that end to ground. Now for this circuit, the input is 0.5 sin omega t of frequency 1 kHz. So give 0.5 amplitude sinusoidal signal of frequency 1 kHz from function generator and observe the output voltage on CR. Now we can see that the output voltage is gets amplified than the input one. And note down the V0 and Vi values and find out the differential mode gain. And you can see that AD is more compared to AC. So from this AC and AD values, whatever we have measured, we will find out the CMR, common mode rejection ratio, which is the ratio of AD and AC. And we will see that AC is very less and AD is very high, so CMR is very high, of the order of 10 to the power of 4.
As of now, we have been looking at linear circuits where we ensured and assumed that the output did not saturate either to plus VSAT or to minus VSAT. Now, we want to use the op-amp in a very different way. What we will do with the op-amp is to use it to compare voltages. And let's see how it performs, what its weaknesses and its strengths are. Here is an op-amp circuit where no feedback resistor is provided. So this will act with its full open loop gain. The inverting terminal has been set to 0. So essentially K times Vi is going to be Vo, where K is going to be of the order of a million or so. So you recognize what will happen. If I apply even a very, very small amplitude sinusoid at the input, let us say such as this, the output will be a positively amplified but very heavily amplified version of the input. And because it amplifies so highly, what will happen is for even the smallest positive value of Vi, if this is Vi, the output will directly jump to plus VCC, and the moment the input goes negative, the output will jump to minus VCC, again to plus over here, and so on. So this is VO. This is how this circuit would behave even for the smallest amplitude of input sinusoid or input alternating voltage. As long as the input is positive, however small, the output will stay at VSAT plus VSAT, and as long as the input is negative, it will be at minus VSAT. The output can therefore only assume two possible values, plus VSAT or minus VSAT. No other values are possible. This is how this circuit would work. But then this looks fine. Let's ask what happens if I grounded this point instead of applying a Vi to it. Let me see what happens if I ground this point. I am about to do it. Let me connect this also to the ground. So if it is ground, that means the non-inverting terminal voltage is actually 0. Now if it is 0, what should the output be? Theoretically it should also be 0, but that's not how it works. The fact is that there is always a small amount of noise that is generated thermally within the circuit, in the outside wiring, etc. So that minuscule positive and negative voltages do appear between the inverting and non-inverting terminals even when they are jointly grounded in the manner that I have shown. So even when the input is practically 0, the output would do a wild dance between plus VSAT and minus VSAT, something of this sort. This is what the output would be like when the input was confined to 0, even when the input is grounded. This happens because the 0 voltage is really like a knife edge, and the output cannot in spite of the best efforts, balance on the knife edge. Either it falls onto this side and goes to plus Vset, or falls onto the other side and goes to minus Vset. It never can really stay put on the edge in perfect balance. It just can't do it. And in order to get more predictable behavior out of a comparator, we make the following modification. This modification is aimed at ensuring that when the output makes only very minor variations, when the input makes only very minor variations, the output does not keep jumping around but stays put at one point. And what we therefore implement is the concept of hysteresis. What is hysteresis? You see, a comparator is always understood in terms of the threshold voltage. The threshold voltage is a certain voltage, in this case 0, above which the output assumes a certain value, and below which the output assumes a certain value. And irrespective of whether the input goes downwards from above the threshold or upwards from below the threshold, the switch of the output occurs at the same threshold voltage called Vt. So if Vi is less than Vt, you have output as minus Vsat. If Vi is greater than Vt, the output is plus Vsat. In this case, Vt is 0. So that is how the conventional inverter, the conventional comparator works, which is not what we want. What we want is this. We say that there are two thresholds essentially. If the input moves upwards from below Vt to, rather from below 0, if it moves upwards, then let us say that the output switches when the input crosses plus 1 volt, not 0 volts. Now, until the input crosses plus 1 volt, the output will remain at its previous state. Now, when the input crosses plus 1 volt and becomes more positive than 1 volt, the output will switch to plus Vsat. On the return, when the input starts falling, the output does not switch downwards to minus Vsat when the input crosses plus 1 volt, but does so when it crosses minus 1 volt and remains in the previous state until this happens. So let's say we apply a triangular waveform as the input and see what the output will be when there are two thresholds instead of one. The presence of two thresholds, one for upward going input voltages, input voltage transitions, and the other for downward going input voltage transitions, is what we call hysteresis. So let's make a plot. Here is Vi. And then we shall take slightly exaggerated values of the upward going threshold and the downward going threshold. So let us say the upward going threshold is this, and the downward going threshold is this. Let us also assume, for convenience and without loss of generalization, that in the initial stages, when the input is below the upper threshold, the output is at minus Vsat. Let's say this is minus Vsat and this is plus Vsat. So until the input crosses the upper threshold, the output remains at minus Vsat. Once the input crosses the upper threshold, the output shoots directly to plus Vsat. So the output is now here. Now the output stays here Not until this point, but beyond, until in fact the input crosses this point, which is the lower threshold. So the downward going threshold is this, and it is at this point that the output switches to the minus Vsat value. Again, as we continue, we go on here, and the return to the plus Vsat is not achieved at the downward going threshold but at the upward going threshold. The downward return is at the downward going threshold. Observe this waveform, which is a joint plot of the input. Let me redraw this part. This is the Vi and this is the Vo. Observe that the upward and downward going thresholds differ from one another. How we do this, we will see when we study the Schmitt trigger circuit. Here is the Schmitt trigger circuit. What we have here is positive feedback instead of negative feedback. You would have had negative feedback if you connected a resistor from the output towards the inverting terminal, as we did in the case of the inverting and non-inverting amplifiers. That was for amplifier-like or linear behavior. Here we want non-linear and abrupt behavior. So we want to exacerbate the sensitivity of the already very sensitive operational amplifier by putting this positive feedback on this side. Let's see what it does. Because even minor variations of the voltage difference between the positive and between the inverting and the non-inverting terminals are highly amplified, we can be sure about one thing. The output voltage Vo at any time assumes only one of two possible values, namely plus Vsat or minus Vsat. So for the sake of argument, let us say that the output at a certain point of time is minus Vsat. Let us also ignore, for simplicity, the variable resistor over here. Let's say we just ground it at this point. Then what do we have? This is a voltage divider. 15 kilo ohms, 10 kilo ohms, that means it transmits 0.4 times the output voltage to this place. So if it is, we cannot say it is 0.4 Vsat actually. What we more appropriately should say is that it is 0.4 times Vo. So whatever Vo is, if it is minus Vsat, it will be minus 0.4 minus 0.4 Vsat. If it is plus Vsat, this will be plus 0.4 Vsat. So that's what. As I said, let us assume that the output is at minus Vsat at some point of time. So that minus 0.4 Vsat appears at the non-inverting terminal. Note that the input is being given at the inverting terminal. In the experiment in the lab, you will be experimenting with a sinusoidal input, whereas for ease of drawing the figures in this explanation, I am using a triangular input. It makes no difference to the way we understand the behavior of the Schmitt trigger. So this point is at minus 0.4 Vsat. Now, when this is at minus Vsat and this is at minus 0.4 Vsat, the output will switch its state when, instead of having a negative difference between the two terminals, which is the cause of keeping the voltage at output voltage at minus Vsat, there is a positive voltage difference between the non-inverting and inverting terminals. That is to say, when the non-inverting voltage, terminal voltage, is greater than the inverting terminal voltage, which happens when the inverting terminal voltage goes below the non-inverting terminal voltage. the inverting terminal voltage is Vi and it is being applied at the inverting terminal, and the point where it crosses minus Vsat downwards and goes below minus Vsat is the point at which the output will switch from minus Vsat to plus Vsat. And the moment the output switches to plus Vsat, what we have at this point is plus 0.4 Vsat instead of minus 0.4 Vsat. So immediately the threshold that is of interest is not minus 0.4 Vsat but this line over here. This is the new threshold. And as long as the voltage difference between the non-inverting and the inverting terminal remains positive, that is to say, as long as the input remains below plus Vsat, the output will no longer switch. Sorry, as long as the inverting terminal voltage remains below 0.4 Vsat, below 0.4 plus Vsat, it remains at plus Vsat at the output. Now when the input voltage rises and crosses plus 0.4 Vsat as it is doing at this point, again we have a negative potential difference between the inverting and non-inverting terminals, and this causes the output to fall to minus Vsat and the threshold to change to minus 0.4 Vsat. So this is how the Schmidt trigger behaves in practice. Finally, if you connect the scope in XY mode and apply the input on the X, that is channel 1, and the output on the Y, which is channel 2, you will observe the transfer characteristic of the Schmidt trigger to be of this form. You see here that you have output levels VOH and VOL. VOH is nothing but plus Vsat, VOL is nothing but minus Vsat. VIH is the term that determines the point of the input voltage value that causes the switch, and that is 0.4 plus 0.4 Vsat. VIL is minus 0.4 Vsat. So this essentially explains how the output voltage and the input voltage are related in terms of values to each other. This is the transfer characteristic. Let us now finally reintroduce this variable resistor or potentiometer that was connected to this side over here. This is given in the circuit, given in the manual, and we want to understand what it does. This is a 10 kilo ohm rated pot, that means it gives you a maximum resistance of 10 kilo ohms. Any value between 0 and 10 kilo ohms. Let's see what it does. What happens when you set this to any non-zero value? It just changes the ratio of the potential divider. If this had been 0, we knew we had 0.4. If this is larger than that, this changes to 0.5 or 0.6, etc. And thus the threshold voltage, both the upper and lower threshold voltages, are symmetrically shifted either upward to say this place, or either upward and the negative one simultaneously downward to this place, or closer together as here and here. One of these things can happen, but it cannot really shift closer because the minimum of 10 kilo ohms is always there even when this is 0. So all this potentiometer setting will do is to shift the threshold values further outwards. The upper threshold goes up, that is to say VIH moves to a greater value and VIL moves to a lesser or more negative value. So that is the function of this, and thus can be checked. You put the oscilloscope in XY mode, apply VI at the channel 1 and VO at channel 2, get the transfer characteristic on the screen and turn this potentiometer and see what happens in real time. This will tell you what is the effect of this potentiometer on the behavior of the circuit.
Now we will see how OpAmps IC can be used as Smith trigger. Smith trigger is basically a sine to square wave converter. So it is used in wave shaping applications. Now in the Smith trigger we use positive feedback and the output will be either plus at Vsat or minus Vsat. Now this is the circuit connections are already made here as per the handout that is given to you. For this circuit 8 volt amplitude and 1 kHz frequency sinusoidal signal is to be given from the function generator, and we can observe that input signal here. We will measure it now. Okay, it's around 8 volts. Now this is input is given in the channel 1. Now we will see in the channel 2 the output of the circuit. Now this is the output of the Smith trigger circuit. This is basically a square wave. You can see that input is sine 1 and this blue waveform shows it's in channel 2. So this is a square wave. So sine wave is converted into square wave. Now we will see in the XY mode the graph of V0 versus Vi. So we can see that this is called hysteresis. The x-axis is Vi, input voltage, that is input sinusoidal signal, and this y-axis is output 1, that's a square waveform. Now I am going to change the potentiometer, which is shown here. This is potentiometer. I am going to change the value. You can see that as I change the value of the potentiometer, so the hysteresis, the width keeps on reducing and increasing as per the changes in the potentiometer. This we can see clearly. So now width is decreased almost, and if I again increase, this width has got increased. Now, for the two extreme positions of the potentiometer, that is, for the waveform, this width is very less, and for the one width is max, we have to observe and sketch V0 and Vi. And for the two cases, we have to determine V0H, V0H, V0L, VIH, VIL. VIH means this is the input voltage axis. So this is the VIH point, and this is the VIL point, and this is VOH. This is equal to plus Vsat, that is plus 12 volts in the circuit, and this is VOL. So observe for these values, determine these values for the two cases, for width less 1 and maximum 1. Now this completes the experiment 5. Thank you.